So a short video on Hess's law here. Hess's law states that the enthalpy change for a reaction is independent of the route taken. So often you're looking to calculate the enthalpy of the direct route by using an indirect route and adding up their enthalpy values. So the two most common multiple choice questions here. So this one here is looking at 4 different reactions, and we've got their enthalpies written as A, B, C and D, and we have to work out the relationship here. Now, because A is what they're all equal to, A must be the target equation that we're trying to achieve. So A really becomes the equation that's in our box here. So this is the one that we're comparing everything to. Now, when you look at these, you're looking at what's in an equation and what's common with the box. So when we look at this first one here, you'll notice that it's on the left, but we need it over here on the right. Therefore, this equation here, we have to flip. So the delta H actually becomes negative B. When you look at the second equation, we've got a carbon on the left and we need a carbon on the left. So we don't actually have to do anything to that equation. So our enthalpy remains as C. And the final equation, we have hydrogen on the left, and we've got one hydrogen on the left in the target equation. So again, we don't have to do anything there. So when I look at my A, my value for A is equal to the enthalpy of B, which has become minus B, plus the enthalpy of C, plus the enthalpy for D, and these are both positive values. So I'm looking for the combination as a minus B, a positive C, and a positive D. And when I look at that, you'll see that A has to be my answer there. The next multiple choice question, again, common for Hess's law. Be careful here. They will have the answers for the mistakes that may be made. What we're looking for here is the enthalpy to go from Z to Y. That's a direct route. To go from Z to Y, though, you're going to have to follow the path, the indirect route, from Z to W, from W to X, and from X to Y. So we're looking at the direction of the arrow is important here. So because we're going from Z to W now, we've flipped the arrow round. Therefore, we'll have to flip the sign, and this now becomes 210, positive 210. Look at the next one, we're still going the same direction as the arrow, therefore we're still negative 50. And then for this one here again, we're still going the same direction of the arrow, therefore we're still negative 86. So when we come to find the enthalpy for the question mark, we've got positive 210 plus negative 50 plus negative 86. And when you add those together, you get the value of 74. So it's making sure, so the answer is A there. So it's making sure that you're noting if you flip the arrow direction, you have to flip the sign. Right, next I've got a couple of calculations then. So Hess's law calculation, if I move this a wee bit, you're given the equations here and you're given the enthalpy values. So the first thing I want to do is I want to identify what I'm trying to calculate here, and this is my target equation. This is what I'm trying to find the enthalpy value for. To do that, I need to use the 3 equations that are given to me. So again, what I'm looking for is what they have in common with the box. So the first one I'm looking for here is carbon monoxide. So carbon monoxide is in common with the box. You notice I've got one on the left and I want one on the right. So what I'm going to do to this equation is I'm going to flip this equation. So I'm going to flip equation number 1. And that means my enthalpy value becomes positive 283. The next one I'm looking at is the hydrogen. Hydrogen here and hydrogen here. You'll notice the hydrogen, again, it's on the opposite side from what I need, so I'm going to have to flip. But I've also got a big 3 here. I need 3 hydrogens and I only have 1. So for this one, I need to flip and multiply by 3. And when I do that, I become a positive, and I'm 726. And then the last one here, I'm looking at the CH4, CH4. I need one on the left, and I've got one on the left, so I don't have to do anything there. So my value becomes the same as it was before. So when I come to look at my delta H, it's the enthalpy change for number 1, so I've flipped it to become positive 283, plus the enthalpy change for equation number 2, I've flipped and multiplied by 3 to give me positive 206, plus the enthalpy change for equation 3, which I've left the same, so minus 803. And when I add those values together, I get 206. It's given me the units of kilojoules per mole, so technically I could leave it as 206. If I choose to put the units in, I must make sure that my units are the same as given in the question. Last one, I've put a wee trickier one in here just so that we can have a look at this. Again, if they decide to make this a trickier question, then there are some kind of problem solving aspects you need to consider. So again, I'm looking here at my boxed equation, and my boxed equation is what I'm trying to calculate my enthalpy for. So if I look at this here, here's what I have in common. I've got this one, I've got H2O2, I've got H2O, and obviously they both come from here. So when I look at this one here, I've got one on the left, one on the right, and that's what I've got, so I'll leave this the same. Okay, so my value is still 177.4. I then look at my second equation, H2O2 on the right, but I need it on the left. So my second equation, I'm going to have to flip. So that's going to become positive 191.2. Now I'm going to leave this just now until I sort out what I've got here. So when I look here, I need 2 waters on the left, and I've got 1 water on the 2 waters on the right, sorry, and I need 1 water on the right. So all I have to do to this equation is multiply this by 2 and keep it on the same side. So it's still negative, but it's negative 87.6. Now when I look at this one here, it's not in my target equation, but you'll notice it's got this equation here that I do need the liquid water, has got water in the gaseous form present. And I need to cancel that out because it's not in the boxed equation. So I've now multiplied this up. So I now have a 2 in front of this and a 2 in front of that. So for me to be able to cancel these gaseous waters out and get rid of them, I need to be able to cancel with this gaseous water here. So I do need this equation to get rid of this gaseous water. I need 2 gaseous waters so that I can cancel them out here and here. So actually I need to multiply this equation by 2. Don't have to flip it. I want them in that side to cancel out with the opposite on the other side. So that's still negative, and it's 83.6. So when I add these together, my delta H value is 177.4 plus 191.2 plus negative 483, keep that again, 83.6 and plus negative 87.6. And when you add that together, you should get a value of negative 202.6. Again, they give me the units in the question, so if I decide to put them in, I need to make sure they're correct. So that's a trickier version of the Hess's law there, where it may appear that you don't need an equation, but in actual fact, we did need that to be able to cancel out the gaseous form from the liquid water equation that we did need.